Hope the rest of you guys who are watching this are enjoying your grad skip day. I'm sorry the weather is not as awesome for you as it could have been, but hopefully, yeah, you enjoy your skip day. Here we go. So, and I'll just talk to those of you who are actually here. The kind of odd jump. So we did voltage yesterday. I don't think any of these guys have signed up for, no. Thanks, Jordan. And Emily. Unless you did. Did you guys want coffee? Okay. So yesterday I introduced you guys the concept of voltage. The route that we take with voltage is we start applying it to various electrical objects, machines, for lack of a better word. And so we get stuff that ends up looking like this. For reasons that will become obvious in a bit, one of the most important problems to at least start with is this idea of the parallel plate problem. So what the parallel plate problem is this, is you take a set of conducting plates. Ooh, who we got? AJ, good morning, sir. If you were on a game or on a reality TV show, which reality TV show would you be on? You don't know any. Survivor, Amazing Race, Wipeout, can't Wipeout. Okay. American Ninja Warrior. Okay. The parallel plate problem. Basically what you do is you take two large flat metal plates. Okay, AJ, my plan for today is this. I'm going to do lesson 6 and 7. I combine them as one lesson for those of you guys who are here, and then the rest of the class is for you guys to work whenever you want. Two large metal plates get charged up using a power supply. So the circuit's not complete, but the power supply is used to set this thing up. Usually one plate is labeled for a higher voltage, charged to a large positive voltage, and the other plate labeled for a lower voltage is left grounded. So typically it's at 0. Typically what these things look like are 0 is what these minuses are, and then this is charged to whatever positive voltage that the question requires. So if you did this from the wall, you've got 3 slots there. One of them is typically grounded, the circle at the bottom of the outlet. And then you've got, I think it's the one on the left, that's typically charged to, like the difference between then the two is 120 volts between the left and the right. I'm pretty sure the left one is hot. But I have to bring my voltmeter in to check that out. If the metal plates are very, very large, then one of the interesting things that results is that the voltage varies directly with the distance from the plates. So if the bottom is 0 and your max voltage up here is, well, whatever V is. Good morning, Abigail. How are you? If you were going to be on a reality TV show, which reality TV show would you be on? Yeah, you. No, it's not a reality TV show. The sitcom. Ooh, that's another good question. You can think about it, let me know. Okay, so metal plates are going to vary, or if they're large, the voltage varies directly with the distance from the plates. What that means is this. If the bottom voltage is grounded, so 0, and the voltage at the top is 50, to vary directly with the distance means halfway through, the voltage is going to be 25. And this requires large plates. That is going to change relative to the question that you're dealing with. Yeah, even like 2 plates the size of my hand, assuming they're close enough together, it's relative to the distance between them. So the distance between them is really, really small. Any plate of any size could be considered really, really large. But if the distance between the plates gets large, like one of the applications of this that we're going to look at is thunderstorms. So because the distance between the ground and the clouds is so large, the plates, i.e. the surface of the earth, and the cloud cover have to be incredibly large because the distance between them is so big. So it's large is relative to the distance between them. So if we've got plates separated by 5 millimeters, charged to 500 volts, so that's not a very large distance. Here to here is 5 millimeters. You've got 500 volts on the top plate and 0 on the bottom plate. And then every millimeter that you jump up, 1 millimeter, 2 millimeters, 3, 4, 5. Every millimeter you jump up is going to be a 100 volt potential difference. We can graph that, as we do. We're going to graph the voltage as it relates to the distance. 1 millimeter, so this is going to be 100, 200 volts, 300 volts, 400 volts. At 1 millimeter, we're at 100. At 2 millimeters, we were at 200. 3 is 300. 4 is 400. 5 is 500. And so you get a line, looks like this. And as always, when we're doing stuff like this, the question becomes, what do the area, what do the slope represent? In this case, the area isn't going to be super useful. It's the slope that we're going to analyze. So slope equals rise over run. So we've got 500 over 0.005 meters, 500 volts over 500.005 meters. It's going to give us a slope of 10,000 volts per meter, which isn't super useful until we analyze what volts and meters actually are. So if you look at what voltage is, we had an expression for finding voltage yesterday. I can find my formula sheet. Where did my formula sheet go? That's unfortunate. It's under the blue book. Ah, yep, it's tabbed. There we go. So the formula we had, one of the formulas we had for finding voltage yesterday was this one here. KQ over R. And if we're dividing voltage by meters, so volt per meter, is going to give us this KQR over R. So KQ over R is going to give us KQ over R squared. We've seen that expression before. What is it? That's the electric field. So now all of a sudden, the slope of this graph as voltage varies with distance gives us the strength of the electric field between these two plates. An interesting effect is that this voltage, as it increases and as the distance increases, the slope remains constant. So the result then is, it doesn't matter where you are between these two plates, as the voltage is increasing, what's happening to the electric field? It's constant. Because the slope of this graph is constant, means the electric field is constant between these two plates. Doesn't matter where you're at. So that's a useful result that we're going to write down. The electric field is constant everywhere between two charged plates. An interesting result. Once you got that down, flip the page. So we're just going to draw that out. If this is 0 and this is 500, as my voltage increases, 300, 400, the electric field's going which way? AJ, you're saying electric field goes down. That is positive at the top, yes. So down. Electric field goes out of positive charges and into negative. So if this thing is charged positively, my electric field's going out of that plate down into this plate. That doesn't complete the circuit. Like, Don't confuse the electric field that exists between these plates as somehow completing the circuit. It's not. But basically, you can think of this as being it's like a capacitor. It's charged, that's charged, and there's no charge being dissipated here. There's no electrons flowing here to complete the circuit. But you've got an electric field that exists between these two plates. And that E field is constant. It doesn't matter how close you are to either plate. The electric field is constant everywhere in there. And analyzing the units for the slope gave us the expression that the electric field E is equal to the change in voltage V over the distance between those plates. So that delta V is voltage difference, and D is the distance. This is interesting, the voltage difference, in that it doesn't matter what your voltages are. All that matters is the difference between them. So the bottom could be 0, the top could be 500. Or you could have negative 250 and positive 250. The difference is still 500 volts. Doesn't matter what they are individually. It just matters what the difference between them is. And that's going to make some of the problems that we look at really, really easy. So if I wanted to find the electric field and the direction inside these two plates, if one was charged up to 225 and the other one's grounded at 0, and they're 3 centimeters apart, then the electric field between them is just going to be equal to E equals delta V over D. The voltage difference is 225. Their distance has to be in meters, 0.03. So then the electric field is what? And the units are what? Volts per meter. I don't know which way north, south, east, west is, so easier would be to say that it's to the right. By analyzing these units, you can create all sorts of interesting things. Just kind of a bit of a side note. We had electric field now is volts per meter. Electric field before was newtons per coulomb. So now M is meters. If we rearrange this thing just for fun, this is not a requirement, but this is just for fun. You can measure volt coulomb per newton is now a meter. So now you can measure distances in volt coulombs per newton. Does it make sense? No. But you could do it if you wanted to. When we get to magnetism, there's going to be a unit called a Weber. We'll get there, hopefully. And you can actually use Webers as a unit for speed on the highway, which, again, is odd and not something we would ever do. But playing with these units allows us to start doing some interesting things. This is totally an aside. Flip page. Oh, yeah, Jay. No, they definitely don't exist. But you could make them if you wanted to be just one of those engineers. Example 3 isn't one that I'm going to go through. We'll talk, we've said it already. How does the electric field at point X compare with the electric field compare with the electric field at point Y? And we've already said it. X and Y is going to be the same because the electric field is the same everywhere between two parallel plates. Not this year. The parallel plate problem is one that comes up and everywhere, and you'll deal with the parallel plate problem in more interesting arrangements next year. Well, if you take this in second semester, is typically when the second semester of year 1 is when E&M starts. Typically they alternate. Like we had the first half of our course was kinematics and dynamics. The second half is, which can be lumped together into what's called mechanics, the physics of motion. how things move, whether anywhere in any space, and then E and M. And typically what universities do is they, instead of breaking one course up half and half, universities will say the entire first semester is all mechanics. You'll look at momentum, moments of inertia, circular motion, especially first year. First year's gonna look a lot like Physics 12, except you're gonna use calculus to do everything. And then second semester is when they start E&M. And then so year 2, first semester is mechanics 2. And second semester, year 2 is E&M 2. And then mechanics 3 and E&M 3, and it just kind of builds that way up. I stopped taking mechanics after year 2, and I took E&M all the way into 4th year, just because I found this stuff super interesting. One of the things to make sure that you keep straight is between parallel plates, the E field is constant, which we've established. E field is constant in the plates. I'm not going to write the in the plates part because I wrote it in the plates. Between or outside of a charge, between 2 points in space, what happens to the electric field? As I move, if this is my charged object, as I move from X to Y, there's nothing over here. What does the E field do? Yeah, it falls off. The E field gets weaker. Because over here, the electric field that was given to us using this formula, delta V over D, there is no variable there. That's a constant between everything. But outside of a charge, you get E equals KQ over R squared. This is for plates. This is for outside of any charged object. And you can see that R squared in the bottom means as you get further away, it's going to get this part of that term is going to make this whole thing shrink. Okay. Tongbean, good morning. This is how these graphs tend to look. If I were going to graph voltage and distance between 2 plates, the voltage drop is a straight line. They're equally proportional. Voltage outside a charged object drops off like this. These slopes are the electric field. So here you can see the slope remains constant. Here the slope starts really big and gets small. For both of these, the slope equals E. And then there's some analogy stuff on the bottom that I typically don't go through. How do you feel about the concepts of voltage and electric field? They're kind of making sense? Okay. Then this is where there are some questions. I skipped straight to lesson 7 at this point. I mean, lesson 6 took us all of 10 minutes. Just introducing the concept of electric field between 2 parallel plates, and now we're actually going to use them. So flip to lesson 7 on page 392. We're just going to sum this up. We're just going to redraw it in here. This is probably the 6th time I'm going to say it in the last 10 minutes. E field, well, the E is constant between plates. Between plates. And given to us by that formula there. So, first example. The things that we typically tend to try and do with these plates, there's a whole ton of different applications to them, but ultimately what we end up using them for is to deflect or manipulate charged particles. Because if I set up a system that looks like this, I can generate a fairly large electric field very easily. All I got to do is crank up the voltage. And there are machines that are designed, power supplies that are designed to do this relatively easily. So typically there's a dial on them, you crank it up. You can create a massive electric field in here fairly easily. Make this distance pretty small, make the voltage difference pretty big. And now if we start sending particles through them, we can start manipulating those particles. So an example of that would be something like this. If I take an atom and I send it through something like this, where I've got a large electric field, what's going to happen to these pieces of the atom? Well, one gets pulled in the direction of the field and the other one doesn't. Which one gets pulled in the direction of the field? Our definition for the direction of an electric field was the electric field is moving in the direction that a positive test charge would move if placed at that point. So our large electric field is moving to the right. So which of these two particles is going to follow that path? The positively charged nucleus full of protons and neutrons, or the electron? Our definition for the electric field said the electric field is moving in the direction that a positive charge would. So the nucleus is what's going to go to the right here. So there would be a force on this guy that way, and the expression for that force would be Fe equals what? What was the expression for a force on a charge in an electric field? So just like the force on a mass in a gravitational field. Force on a mass in a gravitational field is mg. So the force on a charge in an electric field is in electrostatics, mass is the same as the amount of mass is the same as the amount of charge. Yeah, thank you, Toby. And the gravitational field has what analogous thing in electrostatics? I'll write this down up here. Fg equals mg. So Fe equals charge times, this was a field. What field are we dealing with here? Yeah. So Fe equals QE. This guy right here. All of these different equations represent specific scenarios. This is a force between two charged objects. This is the force for a charged object in an electric field. So that's the one that's going to be useful for us here. And now we've got this expression here. This is for plates. And plates specifically. So Fe equals Q times E. So that positive nucleus is going to want to go to the right. The negative electron is going to want to go which way? To the left. Fe equals QE. And what's the expression for the force between these two things? F equals, because the negative electron and the positive nucleus are attracted to each other as well. That's why they existed this way. So what's that force there? KQQ over R squared, Q1, Q2, we'll call it. So as long as you make the electric field large enough to overcome this force, you can rip apart the electron and the nucleus relatively easily.
You don't have enough, but still pull like just the entire thing in the direction of the electrical field, or would it remain?
If it's a neutral object in an electric field shouldn't interact.
So, but then if you had an ion, would it have to?
But you're going to, oh, absolutely, yeah. Because then you're dealing with the positive charge or the negative charge. It's, yes. Like, so if I shot this guy through this, my electron's going to rip, well, that would get interesting because there would be some movement anyway. What would the partial positive and partial negative do? I think it would, ooh, it's an interesting question. My gut says the whole thing would move in the direction of the positive because you get a partial positive and a partial negative. And depends on the atom, but the force on the nucleus is going to be larger than the force on the electron, but the electron's mass is really small. I don't actually know the answer to that question. There's a lot of things that could determine what's going on there. So if I shoved this particle, a positive nucleus and a negative electron, through here, what you'd end up getting, if I just dropped it in here, is you get one particle going up. This is the path the electron would follow. And my nucleus would go this way. If I took this and shoved them up in there. This has all sorts of useful applications. Let's say you wanted to create an electron gun for whatever reason. Or you want to create a proton gun, something that just shot streams of protons. All you would need is a source of hydrogen that you could run through an electric field, and it would be really easy to separate the electrons from the protons. Proton gun or an electron gun is effectively what you'd need in a particle accelerator. An electron gun is what powers those old tube TVs there. So relatively easy to do, again, assuming you can create the difference in those plates. Another application of ionizing something like this is in a thunderstorm. Because what you've got in the thunderstorm is you've got a large plate on the bottom, and we're going to talk about thunderstorms in a little bit more detail. Not a lot more detail because it's still really confusing as to why lightning happens the way lightning does. We still don't really know, and there's like 4 or 5 different kinds of lightning. But we're going to talk about it in general. Typically what you've got here, though, you've got grounded, so no voltage, or it might be positive, and you've got some voltage in the clouds. That creates an electric field between the earth and the ground. And it depends on the charge of the cloud. It depends on the charge of the ground. The electric field could be going from ground to cloud. It could be going from cloud to ground. Different situations will create either effect. It doesn't actually matter which way the electric field is going. What matters, though, is that this is going to generate it. You've got a whole bunch of particles in the air. You've got stuff like O2, you've got N2, and as the electric field between cloud and ground gets larger, what's going to start to happen? N2 looks like this. O2 looks like this. During a thunderstorm, what's going to happen? As this gets larger and larger and larger, these guys could get ripped apart. Now, all of a sudden, if these guys get ripped apart, you've got theoretically extra free electrons floating around because nitrogen just wants to be neutral. When these guys get ripped apart, do we have any chemists? Do we take chemistry? Okay. There is, I want to make sure I get this right. Where's the, maybe got more energy released when the bonds form, not when they get ripped apart. Either way. As the electric field gets large, these bonds are going to start to break down. That's going to create noise, a lot of it, in the form of thunder. Because it's when all of these start to break down at once is you get a path for free electrons or other charged particles to flow, and you get lightning strike. It used to be in Science 10, now it's in Science 9. You guys talked about the nitrogen cycle? So the carbon cycle is the flow of carbon through the environment. It's vital for cellular respiration and photosynthesis. That's carbon cycle. The nitrogen cycle is you require nitrogen to get into the soil. Nitrogen gets used a bunch of different ways, makes ammonia and ammonium. All that flows back out. It gets denitrified goes back into the environment by bacteria. One of the key parts of the nitrogen cycle is that first stage, the nitrification of the soil. That can happen a few different ways. Beans, for example, are really good at nitrifying soil. Another way, though, that nitrification happens is when something like a thunderstorm rips these guys apart, allowing nitrogen to react with other molecules in the air to create ammonia. So you get, through a lightning strike or through a thunderstorm like this, the process of nitrification occurs. So it's just a connection between Science 9 or Science 10 whenever you learned about or you're supposed to learn about the nitrogen cycle and the stuff that we're looking at now. So an interesting application of parallel plates. So if we're talking about air, it takes about 3 million volts per meter to produce ionization. So that sounds like a lot, but it is and it isn't, because it's 3 million volts per meter depends on the distance between your plates. So maybe your plates are relatively small. You get your hand next to a Van der Graaf generator. You get pretty close together, and the sparks are going to start to jump. Effectively, what's happening there is the air is being ionized between your grounded hand and the negatively charged plate. Because you're so close together, that 3 million volts per meter doesn't take much, because the distance is really, really small. So you don't actually need that much voltage to create that 3 million volts per meter. Or the same thing, when you reach out, you have stocking feet, you drag your feet along the ground, and you reach out for someone's hand, or you reach out for the doorknob, and there's a small jump there. Again, the jump is so small, so your finger makes a decent parallel plate, and you get the sparks that jump there. Again, because things are so close together, that 3 million volts per meter isn't, well, it's a lot, but the voltage isn't actually that high, because the distance isn't that high. But when you get something like this, that distance is many meters sometimes as many as a couple hundred meters. So to get 3 million volts per meter, hundreds of meters away, now you're dealing with a catastrophic amount of voltage. Flip the page. So the reason that light shows up, so lightning, you can see what's going on here, is what Hannah mentioned before when we were up looking at the Van der Graaf generator, and the Van der Graaf generator is interacting with that the neon tube. As electrons get energized and then fall back into an orbital shell, if you guys remember chemistry, if you've taken chemistry, the act of those electrons jumping up and jumping down, getting energized and then falling into an orbital, releases different wavelengths of light. So that's that is what is creating the light that you see when a lightning strike occurs. The light occurs because ionized electrons don't remain free. They quickly fall into an orbit around a neighboring atom. So they might ionize another oxygen atom, or they might form ammonia in the atmosphere. When the electron does this, some of the energy is converted to light. So you get something that looks like this. The bottom of a cloud is charged to 2.5 times 10 to the 8 volts by cosmic rays that pass through the atmosphere. That could be one cause. There's a whole bunch of different causes for the charging of those clouds. Sometimes in a cloud, I'll talk about it after. So let's assume the cosmic rays are the charge. Cosmic rays are just charged particles that are coming from the sun. They're making their way through our magnetic field. They enter the atmosphere. They charge up the clouds. How close does the cloud need to be to the ground for the lightning bolt to occur, assuming this is the charge? Knowing that the air breaks down or ionizes at 3 million volts per meter. As soon as it ionizes, that's what creates the path for lightning to flow, completing the circuit between the ground and the earth. So we know, an application of this, that the voltage in the clouds is 2.5 times 10 to the 8 volts. What we want to find is this distance here. And we're told that air breaks down when the electric field is about 3 million, 3 times 10 to the 6 volts per meter. So we know that E for parallel plates, and clouds and the ground are just effectively parallel plates. E is delta V over D. We know that the change in voltage between the ground and those clouds is 2.5 times 10 to the 8 volts. I want to find D, and I know that E is 3 times 10 to the 6 volts per meter. So what's D? Yeah, AJ. Yeah, ground is, yeah, we'll say assume the ground is grounded. Yeah, that's what I got. 83.3 meters. So 83 meters is like 240 feet. That's like a 24-story building, give or take. Let's say a 20-story building just to be safe. Not very high up, all things considered. So assuming that that's the charge, we know this is just a statement of fact. Air breaks down at 3 million volts per meter. That's the distance that you'd have to have. We could work this the other way too. We could say, what is the charge or what does the voltage on the Van de Graaff generator have to be if it's going to shock you from a distance of a couple centimeters? We could go the other way. Van de Graaff. If that's the Van de Graaff generator, and let's assume that's your finger, the distance here is what? Some of them were only a couple centimeters. Let's say 2 centimeters. If that distance is 0.02, and the air breaks down with an E field of 3 times 10 to the 6 volts per meter, what does the voltage difference have to be between the generator and your finger to cause that spark to happen? Well, it runs the same way. E equals delta V over D, except now we know E and D. We know that the electric field is 3 times 10 to the 6. Let's say that that jump was, or maybe, you know what, let's increase it. What was the largest jump we had? Was it like that? Between Zach and, yeah, it was like that. So what is that? What's the voltage difference have to be for, that's a 6 centimeter jump, give or take. Let's make that 6 centimeters, 0.06 meters. What's the voltage have to be for that? Delta V is, you said 180,000. So the biggest one we saw was between Zach's keys and was someone walking by. It was Ashton walking by? So that means the voltage difference between those two at that point in time was 180,000 volts, which is substantial. Even varying this by a centimeter or two is going to change this number a great deal, but that gives you a perspective on the Van de Graaff generator and now you know what 180, well, Ashton knows what 180,000 volts feels like. An application of this another application of this is a situation like this. If you have charged clouds, clouds charge a bunch of different ways. Sometimes it's the updraft, and updraft is just air rising because hot air rises, cool air comes in and takes this place, and so you get this updraft that happens in clouds. Typically what that does is heavy objects in clouds tend to fall, light ones tend to rise. So you might have snow up there that hasn't melted yet to form raindrops to fall. So there's things moving around. Typically what happens is as these things are bumping into each other, the positive charges rise and you get negatively charged water that starts to fall to the lower end of the cloud. So typically you actually get a large negative charge in part of the cloud and a large positive charge in another part of the cloud, which is why lightning strikes from cloud to cloud. Sometimes lightning strikes within the cloud. You just get those big sheets of lightning. You don't actually see any forks of lightning. But sometimes if you get that big negative charge at the bottom of the cloud and Earth is grounded, there's a huge voltage difference there. That's what causes lightning. Another form of lightning to strike. Lightning is actually that's the wrong way to start that sentence. Lightning is really misunderstood. We don't actually know. It's an active area of research. I did a little bit of research on the weekend just to prepare for this lesson. lightning, we don't really know what causes a lot of the different kinds of lightning. But that is, we do know that what I've described is part of it. So, an application is where do you want to be in a lightning storm? We know, let's assume that our cloud is charged to 2.5 times 10 to the 8 volts. And we know that, based on the previous question, that a distance of 83 meters is all we need for the air to break down and that lightning strike to occur. So look at this scenario. Where do you not want to be? You don't want to be here. You don't want to be anywhere near here. You don't really want to be here either. Sorry? No. Because if we look at how the electric field varies between here and the top of the mountain, the cloud and the mountain, how is that electric field going to compare to this electric field? Where? Yeah, the shorter the distance, the larger the, you can think of it as like a voltage density, the volts per meter. You're going to have a large E here. You're going to have a small e here. Between here and here, you're going to have a large E. Sorry? It is a large tree. It's clearly not to scale. In a storm, so you're actually out on the water. Blake, I know you fished. Any of the rest of you guys have been fishing? AJ fishes, Toby's been fishing, Abigail, you've been fishing? Once or twice. Standing in a boat with a fishing rod effectively makes you a phenomenal conductor. There's Blake fishing in a, well, underneath these clouds. How does, we got 3 electric fields here. Between the clouds and the top of Blake's fishing rod, or AJ's fishing, or whoever's fishing rod, the clouds to boat and clouds to water, where's the electric field going to be the largest? Yeah. E field here is going to be greater than the E field here, which is going to be greater than the E field here. So the most likely place for lightning to strike is where? Yeah, the tip of that rod. Yes. Yes. Because it's going to take the path of least resistance. So yeah, even a small distance like that is absolutely going to make a difference. It's why if you're golfing, golfers tend to get struck more than anything else on the course because you have large open areas. Trees are not super conducive to golf, especially if the course you're on is pretty flat and not on a hill or whatever. Even a little bit of, again, lightning's all about the easiest path. And it will, I mean, have you seen videos of forks of lightning? Okay, I'll show you one later, Gersa Hill, but you can see it in slow motion as it paths its way through the sky, looking for the easiest way down. And then once it makes a connection, that's when the bulk of the ionization happens. I'll show you a slow motion. Have you seen a slow motion video of lightning? I'll show you. Well, I'll play one in a bit here, just to show you that path. That distance absolutely makes a difference. This is why, though, in cities like Vancouver, especially downtown Vancouver, lots of the buildings have, for safety reasons, they've got lightning rods on the top. Because the most likely place for lightning to strike in a storm is going to be the tops of any of those buildings. So one of the things that they engineer into the building so that it doesn't just hit the building and then zap its way through the electrical network, all the copper wire in the sides of the building, what they do is they have a lightning rod that they directly connect to the ground, bypassing all of the building's wiring. So you don't blow out the wiring every time a lightning strikes the building. So that you have this tiny distance here, That's where the lightning's going to strike consistently compared to everything else around it. And then they wire that thing straight to the ground, bypassing all of the internal wiring of the building. A really simple application of the parallel plate problem. Questions? Okay, flip the page. So, keeping in mind, remembering what we had here before, we had F equals Q times E, which we've used before. Let's look at example 4. We want to find the acceleration of an electron placed in between metal plates that are separated by 2.5 centimeters and charged to 275 volts. So, first for this question, we're going to ignore gravity. We're going to look at how gravity relates to this in a second, but for this particular question, we're going to ignore gravity. We're going to find the acceleration of those plates. The acceleration of the electron in those plates. So if I want to find the acceleration, where am I going to start? Acceleration is going to lead us to one of two locations in the course content. Yeah, it's either going to be it's a dynamics problem, F net equals ma, or it's a kinematics problem if I'm asking you for the acceleration. So I've got an electron with a mass in an electric field. The electric field is going to generate a force on our object. So if I ask you for the acceleration, where should we start? Yeah, we're going to start here. F net equals ma. If we ignore gravity, what's the net force on our object? The electric field. Comes from the E field. So from the E field, we know that the force on a charge is equal to the charge times the strength of the electric field. So we're going to get QE equals MA. And where are we going to get the strength of that electric field from? So we're going to get this expression here. Q delta V over D is equal to MA. And now we can fill in all the information we know. We know the charge on an electron is, again, because we're dealing with forces here, we're not going to include the positive or negative on the charge. That's just going to tell us the direction it's going to go. So it's an electron. So that's 1.6 times 10 to the negative 19 coulombs of charge. The change in voltage is 275 volts, and the distance between them is 2.5 centimeters, which is going to be 0.025 meters. That's going to equal the mass of my electron, 9.11 times 10 to the negative 31 times A. So what's the acceleration here? It doesn't matter where it starts. The electric field is constant anywhere. It can start the electron can be placed anywhere in there. Because the voltage difference is not between the plate and the electron, it's between the two plates themselves. And the electric field's constant everywhere. 1.93 times 10 to the 15 meters per second squared. Which direction, AJ? Yeah, the electron's going to go, because it's negative, it's going to go towards the positive plate. Let's do it again, but let's include gravity, just so I can show you why we ignored gravity. Let's include gravity. So we've established that the force on the electron is going to be up, so gravity is going to be down. So the only thing that changes here is I'm going to get this term, Q delta V over D minus mg equals ma. So we're going to get 1.6 times 10 to the negative 19 times 275 divided by 0.025 minus 9.11 times 10 to the negative 31 times 9.8 equals 9.11 times 10 to the negative 31 A. What's my acceleration now? What is it?
1.93.
Effectively the same. The electron is just so small that this term here has no bearing on the acceleration caused by that electric field. Cool? Comments, questions, concerns? One more example. I've actually done this one. This is called the Millikan experiment. And the Millikan experiment was used to measure the charge on the electron. This is how we found out what the value of an electron was. Parallel plates were used on a charged oil drop. The oil drop remained in place because of the electric force balanced with the gravitational force on that drop. There was a little bit more to it than that, but that was basically the setup for the experiment. The oil drop was given to give the whole thing some mass so that gravity would actually have something to interact with, and it was charged up. For it to be balanced there, what does the charge on that oil drop have to be? No. Looking at how we've got this thing set up, the bottom is 0, the top has some positive voltage there. Which way is gravity going to act on that oil drop? Down. So to suspend it, I need an electric force upwards. It's the only way this thing's going to remain suspended. Which way is the gravitational field? Sorry, which way is the electric field going between those two plates? Positive to ground, yeah, top down. That's E. So in order to hang there, what does the charge on the the oil drop have to be? It's got to be negatively charged. We know that the thing has to be negative. So we don't have a ton of detail there. There's an example on the next page, but I'm just going to write it down. We're actually going to do it right here because we've already started the drawing. So here's the information. Let's say our oil drop has a mass of 2.3 times 10 to the negative 14 kilograms. It's a very small drop of oil. And it has a charge Q of 3 electrons. The distance between these plates is 1.5 centimeters. The question is this. What must V be to suspend the drop? So how do we set this thing up? Our force of gravity is going to equal our electric force. Why? We want the acceleration on the object to equal 0 because this thing needs to be in equilibrium. Because we're in equilibrium, my forces down are going to have to equal my forces up. There's one force down, Fg. There's one force up, Fe. We know those things have to be balanced. So we know for Fg is equal to mg. Which force equation am I going to use for that drop in that electric field? It's QE. And I don't know how strong the electric field is, but it's between two plates. So the expression that we're going to use for the electric field is what? Change in voltage over the distance between the plates. So we're going to get mg is equal to Q delta V over D. So we can solve this for delta V. That's going to equal mgd over Q. So now I can just fill this thing in. The mass was 2.3 times 10 to the negative 14 kilograms. The little g, I'm assuming this experiment is happening on the surface of Earth. So g is 9.8. That distance is 1.5 centimeters, which we have to convert into meters. So that's going to be 0.015 meters. And then divided by the charge. We were told the charge is 3 electrons. So it's going to be 3 times 1.6 times 10 to the negative 19. What does the voltage change between those plates have to be? Sorry, say that again. I got a different number. Yeah, I got 7,000. 43.75. Which means you were out by a factor of 10. Did you have that 0 there? What, you were missing a 0 somewhere. Okay, that would be the thing that would make the most sense. Yeah, 7,000 volts is what you need between those two plates in order to suspend that thing there. Okay, that's it. The questions I want you guys to play with are these. 1, 3, 4, 5, 7, 8, 10, and 12. That's it. And then tomorrow we'll look at bigger problems involving this stuff.